All right, in the next set of notes, 940, we're going to look at some definitions of acids and bases. If you're completing this on paper, I would pause this and get your 941 practice available. Okay, so overview, a neutralization reaction, first of all, is also known as an acid-base reaction. It's also a double replacement reaction, and you have an acid and a base that react to form water and a salt. So, for example, hydrochloric acid and sodium hydroxide, these are two common uh, acids and bases, acid base. It's going to combine, and H will get together with the OH to form water, and then sodium and chloride are get together to form sodium chloride. An acid is a substance that makes H plus ions when dissolved in water. So again, so HCl, if you were to combine it with water, what's going to happen is because acid's a very polar substance, it's going to bond. This H is going to bond with this H2O to create, this is called hydronium ion, which will be on another slide here. And then when it loses that H, it becomes chloride. So acids often begin with H, and that's kind of important maybe to note as just kind of a cheat or I don't know, something just to remember. Bases are going to make hydroxide ions when dissolved in water. So, for example, sodium hydroxide, you see the OH at the end here. That's a really good key that this is a base most of the time. When it combines with water, what's going to happen is it dissociates and it becomes sodium hydroxide. Salt is an ionic compound made from the cation of a base and an anion from an acid. So in this case, sodium chloride was our example, but it can certainly be other, ionic compounds. All right, our first definition is Arrhenius acid and base. So Arrhenius acid, this is named after a Swedish chemist. His definition just is probably the simplest. It means that it's going to increase the concentration of hydrogen ions in an aqueous solution. Acids do. So Arrhenius acids increase concentration of hydrogen ions. The acid will ionize in a way that increases the amount of hydrogen ions present. And ionization, remember, is when ions form from a covalent compound, which is slightly different from dissociation. That's when it's ionic. And again, acid molecules are really polar, so thus water molecules attract their hydrogen atoms, and then the extra H plus is going to attach to water, and this becomes hydronium ion, which is H3O1 plus. So here's an example, HClO3. This is an acid because it is, if you see from left to right, it gave its hydrogen to this water, so it became hydronium, and then this is ClO3O1 minus, this is its ion. Here's the general equation. Arrhenius bases are going to increase hydroxide ion concentration. So what we're looking for a lot of times are OH. So you'll see the OH at the end here, and then you'll always see a metal to start out with. This is a metal hydroxide, and they're going to release hydroxide ions in the solution. We say dissociate because typically bases are already ionic compounds, so they only ionize, like we see in acids, if they start as a covalent bond. All right, so sodium hydroxide in the presence of water is going to break up into sodium and hydroxide, and so here's my generic equation. So as a summary, Arrhenius acids are increasing H pluses in solution, and then Arrhenius bases are increasing OH1 minuses in solution. So you're looking for OH in the formula to identify it as a base for Arrhenius, and then often H is going to start out the formula for Arrhenius acids. Here's one other note about Arrhenius bases is that some bases will react with water to remove a hydrogen ion, leaving OH in the solution. So this is a really common weak base. This is called ammonia, NH3. And so you'll notice it doesn't have OH here. So what happens is when it reacts with water, it actually is going to take that H from the water to become ammonium, and then hydroxide would be left over. All right. In our second definition, and by the way, there's 3 total, but we are going to do 2 out of 3. So we have Arrhenius acids and bases. This is our second one. Bronsted-Lowry, again, named after 2 scientists. This is when protons are transferred from one reactant, the acid, to the other, which is the base. So important to remember, highlight, define, is that Bronsted-Lowry acids are proton donors. And when we say protons in acid-base chemistry, we are meaning H pluses. We're not meaning the subatomic particles in the nucleus. They call protons in acid-base chemistry, they're talking about H pluses. So in the form of a hydrogen ion, that's what that means. Bases for Bronsted-Lowry are proton acceptors. So often what will happen is they'll give you an equation and you can look to see what's happening from left to right to figure out who is the acid and who's the base. So if I look from left to right, I am going to actually throw in this term conjugate, which conjugate, I'm sure you're familiar with that, like in different languages. But conjugate, in this case, is a verb. It's a conjugate acid-base pair. And they're just going to differ by an H plus. So if you see like HCl and Cl1 minus, they're just differing by a proton. We always have like 2 conjugate pairs in our equation because we're going to have an acid and a base. So the reason why HCl is the acid, I mean, often it starts with an H, but what you're seeing from left to right is this lost a proton. So it actually is going to give up its proton to the other species. So it's going to give its proton to this water. And you can see water now is hydronium on this side. So this is the acid in this case. Now water is going to be the base because it's accepting. So this is how we can figure out who's accepting and who's donating based on, we look from left to right. Let's do the other one here. So in NH3 in water, if we look from left to right, like we just look at let's go ahead and bracket our conjugates. So if I look from here to here, what's happening is it must have received a proton. It has to receive a proton from the other species, which would be water in this case. All right, so H plus is being donated. So this is going to be the acid. This is the base. So I'll do some more practice with that in a little bit. But you're looking to see who's donating protons. That's the acid. Who's accepting protons. That's the base. All right, so what I mean by more practice is this. There wasn't a lot of practice in these notes, so I added this page. So you will have to add these to your notes. It's not that much writing. So if you, wherever space you have, either if you're doing it digitally or on paper, I would pause the video and maybe just jot these down. Okay, so just as I did before, this is how I'm going to do it, kind of break it down. So I'm going to bracket my conjugates, which means I'm going to bracket things that kind of look similar on either side of the equation. As you can see, like these look very similar. They're just differing by a proton. That's my first step. My second step is to look, and let's just look at one set of conjugates here. Like from here to here, you can see that it gained a proton. So it must have gained a proton from the water. If it gained a proton from the water is donating, that's the acid. The phosphate's the base. Now, we have another term called conjugate acid, conjugate base. That will be on the right side, although it's kind of arbitrary who you define as acid base and who you define as conjugate acid and base, since there's a reversible arrow. But we'll just stick with this format. So if the phosphate is the base, then this hydrogen phosphate must be its conjugate acid. And if this is the acid, this must be the conjugate base. So I could do the proton transfer on this side because I know this is the acid. It's going to give away its proton to the hydroxide. Let's do the other one. So go ahead and bracket the conjugates. And then let's look at what's happening here. This to here, it lost a proton. So if it lost a proton from left to right, it must be donating. It's donating its proton to the other species. So this is the acid, this is the base. If this is the acid, this has to be the conjugate base, and this is the conjugate acid. It all kind of falls in place once you identify one of them. This is the acid on this side. It is donating its proton to this ion right here. So this is very similar, if you're looking at 941 practice, to this part 3. All right, the second part here, we're going to just figure out the conjugate acids and bases. Now, if this is very similar to the backside of the second page of your practice for 941. So there is an example, but I'll do some more for you. So these are bases, and we're gonna find the acids from it. As a note, if this is helpful, what you're gonna do to find the acids, these are the acids we want to find at the conjugate bases. To find conjugate bases, we're gonna subtract a proton. So we're gonna subtract H, we're gonna subtract a plus, which means we're adding a minus. This is going to be adding a plus, H plus. So because what's happening is like these all become acids. Acids have that extra proton. Whereas if these are the bases, or we're trying to find the bases, we're going to subtract that proton because remember, it'll be donated to. So subtract an H plus to find the base, add an H plus to find the acid. So if I subtracted H and a plus from this, I'm going to drop that H. It'll become F, but this is the part that a lot of people mess up. This is neutral right now. There is no charge. If I subtract a plus, really what I'm doing is I'm adding a minus. The next one, subtract an H, subtract a plus. So drop that H. It'll be PO4. Now I have a 2 minus. If I'm subtracting a plus, I'm really adding a minus. So that's 3 minus. Subtract an H, subtract a plus. We're going to have NH3 as my formula, and then it's just going to be neutral. If I subtract a plus, really that's a plus there. It's hard to see, but that's NH41 plus. You're going to subtract a plus, you're going to become neutral. And the last one would be OCN, because we're going to drop the H, and we're going to subtract a plus, which means adding a minus. So that is going from acid to base. The opposite from base to acid, add the H plus back. So this is neutral, or I'm sorry, this is negative right now. When I add an H, it's going to become neutral. Same thing with this one. It's going to become neutral. Just add an H plus, that minus becomes 0. This one, I'm going to add an H. When I add a plus, it's just going to become negative. And lastly, I'm going to add an H. When I add a plus, that becomes 2 minus. Okay, hopefully that helped a little bit. It takes a little bit of practice. I know that there is some interactive practice in the 9-4 folder where it says, do you need more help or practice? So check that out if you need to. All right, the last part here, just some properties of acids and bases. So as we all have experienced, acids can be pretty sour. They could also be corrosive to body tissue. This is like carbonic acid, which is like a soda acid that's in there. And then vinegar is acetic acid. These are pretty weak acids. They're not very corrosive. So these are things that we can consume and use around our house. When you react them with some metals, if you remember active metals, you will get some hydrogen gas being formed. If you react them with carbonates, you'll get carbon dioxide. So for example, barium and sulfuric acid, this is hydrogen sulfate or sulfuric acid. When you react, what happens is barium displaces, these are single replacement reactions actually. It's going to displace or replace hydrogen, kick it out, and it's going to get together with the sulfate to become barium sulfate. This one is acetic acid. When it reacts with calcium carbonate, it's going to create carbon dioxide and water, and then it will also create a salt, calcium acetate. So it reacts with bases to make salts and water and neutralization reactions, as well. So if you have like antacids, I think that's on the base slide, because you have a very acidic stomach, the goal is to neutralize it. Another thing about acids is that they are always electrolytes in a solution. So if you were to test them and with your conductivity tester, you will definitely see some kind of uh, light up to show that there's electric current. They will also cause color changes and indicators. So, for example, litmus paper or pH paper, you're going to get a reddish color. All right, properties of bases. Some of them I wouldn't recommend tasting them, but we've all gotten soap in our mouth before. It is bitter, so there's a bitter taste to them. They also could be pretty caustic and burn body tissue. We often think about acids being very destructive, but actually bases are pretty bad as far as that. Any kind of cleaning products, soaps, um, bleaches, ammonias, those are all going to be basic. They do have a slippery feel to them, and they're going to react with acids to make salts and water neutralization reactions. So this is the antacids that I was referring to. And then lastly, they are also electrolytes because they form the hydroxide ion. Remember, acids will form the hydrogen ion or hydronium. So they will conduct an electric current. They will also cause a color change in indicators. And they are blue. They're going to turn that pH paper or litmus paper blue. And by the way, litmus paper is very broad. It's just going to be red or blue. pH paper, you have different colors, but it's still going to be on the blue spectrum.